So, hello everyone. So, here we'll discuss some problems and try to give their solutions, okay, from real number system, okay. So, the first question is this. So, question 1, let x naught belong to R with x naught is non-negative, and suppose that for every epsilon positive we have x naught is less than epsilon, then prove that x naught is 0, okay. So how to prove this, okay. So it is like this is my 0, okay. X naught is bigger than equal to 0, so I have to prove x naught equal to 0. So if x naught is strictly positive, I will assume it is given that this is less than epsilon for every epsilon positive. So if I choose epsilon equal to epsilon 1, x naught is less than epsilon 1 also, and which is positive if x naught is positive, and if I choose epsilon equal to epsilon 2, which is positive, then also x naught is less than epsilon 2, but at least this picture says that x naught is bigger than epsilon 2, okay. So this cannot happen, right? So what I will do, by contradiction, let x naught is not equal to 0, right? So since x naught is bigger than equal to 0 and x naught is not equal to 0, so only possibility is that x naught is to be strictly positive, right? Now given that x naught is less than epsilon for every epsilon positive, so let epsilon equal to x naught by 2, which is positive because x naught is positive. So by this relation 1 we get x naught is less than x naught by 2, which is false, right? Because x naught is positive, right? So x naught is 0, okay? And this completes the proof, right? This completes the proof. Now we'll discuss another question, which is question 2. The question is like, it says that the supremum of a set of real number which is bounded above has to be unique, okay. So let E is a subset of R be a non-empty set that is bounded above. Suppose alpha and beta are both supremum of E, then alpha has to be equal to beta, okay. So somehow it says that supremum is always unique. So if there are two supremum of a given bounded above set, then they are same, okay. So what is that? Supremum is the least upper bound, right? So we'll prove like this, that claim 1 is we'll prove alpha less than equal to beta. To prove this, since beta is an upper bound of E and alpha is least upper bound, right? Or supremum, both are same, right? Of E, and then alpha has to be less than equal to beta. And this is by definition, right? Upper bound and least upper bound. Least upper bound is always smaller, right? So claim 1 is fine. So this is my equation 1. Similarly, I will prove that alpha is bigger than equal to beta. How do you prove this? Since alpha is an upper bound of E and beta is supremum of E, then alpha is bigger than equal to beta, right? So by 1 and 2 we get alpha equal to beta, and this is the proof, right? Yes, this proves the fact, right? Okay, the next question is very important. This is question 3. So let capital A subset of R be a non-empty set, let alpha belongs to R, so that alpha equal to supremum of A even only for every n belongs to n, alpha minus 1 by n is not an upper bound of A, and alpha plus 1 by n is an bound of capital A. So what is the proof? Okay, so it is giving somehow a necessary and sufficient condition for supremum. Okay, so let alpha equal to supremum of A. Okay, this is a real number. Okay, now what is supremum? If we have a supremum, actually it is a real number, so somehow it exists. It's a finite number, right? So this is my alpha and this is my set capital A. First of all, it is an upper bound, so every element is less than equal to alpha. Second thing is that if I come little less than alpha, or little on the left side of alpha, for example, if I take alpha minus epsilon, where epsilon is any positive number, then I will get some element which belongs to A inside or between this alpha minus epsilon and alpha, right? Between that, which is here, okay, in this open interval, okay, right? So in particular, I can take alpha minus epsilon equal to 1 by n, right, where n belongs to n. Then my alpha minus 1 by n will be here, and I will get some element of A here which is bigger than alpha minus 1 by n. So alpha minus 1 by n cannot be an upper bound, right? So what is the logic? So since alpha minus 1 by n is less than alpha, right, less than alpha, and alpha is the supremum or the least upper bound of capital A, so alpha minus 1 by n is not an upper bound of capital A, and this is true for every small n belongs to n, right? For every small n belongs to n. Okay. Similarly, since alpha is less than alpha plus 1 by n, this is true for every n belongs to n, so alpha plus 1 by n is an upper bound of capital A for every small n belongs to capital N, right? Now, to prove the next part, what we'll do, we'll assume that let for every small n belongs to n, alpha minus 1 by n is not an upper bound capital A and is an upper bound of capital A, right? So I have to prove that alpha is nothing but supremum of capital A, right? So this consists of two parts. One is that my claim 1 will be alpha is an upper bound, right, of capital A, and claim 2 it is the least, right, alpha is the least upper bound of capital A, right? So I will prove first the claim 1. So I know that since alpha plus 1 by n is an upper bound of capital A, so small a is less than equal to alpha plus 1 by n, right? This is true for every n belongs to n and for every small a belongs to capital A, right? And this will give us that small a is less than equal to alpha, right? The question is why, right? If not, then small a is bigger than alpha, right? So then a minus alpha is strictly positive, right? So by the, if you remember the Archimedean property, that is discussed in the previous lecture, and there is also an application of this property. You choose epsilon equal to a minus alpha, which is positive, you can always get some natural number capital N belongs to the set of natural numbers such that 1 by n is less than a minus alpha, and this says that alpha plus 1 by n is less than a, right, where n belongs to n, the set of natural numbers. But this inequality says that this is true for every natural numbers, and in particular I can take small n equals to capital N here. So that will give me that a is less than equal to alpha plus this. But here it says alpha is less than equal to this. Here it's a is less than equal to alpha plus 1 by n. Here it says that a is bigger than alpha plus 1 by n. So this is a contradiction, right? So my assumption that a is bigger than alpha is not true. So apparently small a is less than equal to alpha. Okay, and this says that this is true for every small a belongs to a, and this says that alpha is an upper bound. So my claim 1 is proved now. Okay, now I want to prove that alpha is the least upper bound. So to prove this, I want to prove that, suppose this is my alpha and I want to prove that this is the least upper bound of supremum. So I'll try to take any beta which is strictly less than alpha. I have to find an element which belongs to a, right? Or somehow I have to prove that that cannot be an upper bound. Okay, whatever I prove, okay, that both of us will give that alpha is the least upper bound. Okay, so now to prove my claim 2, what I'll do is that let beta is less than alpha. Okay, so again alpha minus beta is positive, so by using the Archimedean property as we found here, there exists some small m belongs to the set of natural numbers such that 1 by m is less than alpha minus beta, right? That says that alpha minus 1 by m is strictly bigger than beta, right? But by assumption, so I have my alpha here, I have my beta here, let's say. So I found some alpha minus 1 by m, right? Which is bigger than beta and less than alpha. Okay. But by assumption, alpha minus 1 by m is not an upper bound of A, right? So there is some x, right, in the set A which is bigger than alpha minus 1 by m, right? So since alpha minus 1 by m is not an upper bound of A, and this is because of the assumption, right? This assumption, not an upper bound. For every small n belongs to n, so I put small n equals to small m. Okay, this is already used to prove claim 1. Okay, not an upper bound, so there must exist some small x belong to A such that small x is bigger than this and this is already bigger than beta. So I have some x belong to A, that means that beta is less than x where x is in A. So this says that any number which is less than beta, which is less than alpha, cannot be an upper bound. And this says that no number smaller than alpha can be an upper bound of A. And this says that alpha is the supremum of A, which proves claim 2. Okay. So in the next lecture, we'll discuss some more questions regarding